If a seed is planted, it has a 90% chance of growing into a healthy plant. If 12 seeds are planted, what is the probability that exactly 3 don't grow? All right, as with all questions in the lesson 5 and lesson 6 sections, the challenge is to identify which formula would be the most appropriate to get the job done the most efficiently and, of course, correctly. And this is a question from lesson 6, which is all about the binomial probability distribution. Those are random variables that record a number of successes where there's only 2 possible outcomes, success or failure. Now, if you were doing this on the test, the challenge is if you didn't know this was coming from lesson 6 and therefore probably was going to be using the binomial distribution, would you be able to identify that the binomial probability distribution would be the best choice of approach? Well, let's think about it for a moment. If it's binomial, what are the 3 things we can say are going to be true? Binomial random variables. 1, there is a fixed n. 2, there are only success, failure. 3, constant probability of success, meaning the probability of success remains the same for every single trial. Now the fixed n is the number of trials. The success failure is where you look at only 2 possible outcomes, and then the independence is the probability of success. Okay, so if we can identify that these 3 conditions are satisfied, then we can use the binomial probability distribution. And that looks like this, the formula where you can use this to find probabilities. And if you want to use Excel, you can use one of these depending on the problem. There's also a formula for when you want to find the mean or the variance or the standard deviation, the parameters for a binomial random variable, which we don't have in this handout, but it is in the test 2 packet, along with all the other things that pertain to probability in lesson 5 and lesson 6. So knowing that it's a binomial random variable is the first step, and then you have tools that you can refer to in the packet. So let's see if we can say yes to these 3 things. 1, do we have a fixed n? So what we're looking for is a number of times that we're going to repeat an experiment or a process. So here we see that there are 12 seeds going to be planted. So then this first condition is satisfied because n equals 12 seeds to be planted. All right, now, when those seeds are planted, what are the outcomes that could happen? Well, we are looking at whether or not these don't grow. So in thinking about what are the possible outcomes, you could say, well, we know that X is going to record the number of plants that don't grow. And we know that because we are asked to find the probability that exactly 3 don't grow. So that must mean that X is how many plants don't grow. And what we're really saying is we want to find the probability that X is equal to 3. So the success would be that they don't grow. Each time you plant a seed, it'll be considered a success if it does not grow into a healthy plant, because we are interested in getting a certain number that don't grow. I know that sounds counterintuitive because normally you would think of a plant growing as being successful, but you always look at success from the perspective of what it is you're recording or what it is you're interested in finding the probability of. So then the failure would be that they grow into a healthy plant. Okay, so now we have that the first two are satisfied and 3 uh, is also satisfied because we have a constant probability of success for every single seed. So 3 is satisfied because each seed has the same probability of not growing. Yes, because each seed has a 90% chance, or actually a 10% chance of not growing. 10% chance of not growing. Okay, so they told us that the probability of a plant growing into a healthy plant is 90%. Therefore, the chance that it's not is 10%. All right, so then now we're ready to find the probability. So we need our n. To use that probability formula, we need the ingredients that are in this formula here. We need n, we need p, and we need q, we need x. And each of those things are defined right here. N is the number of trials, x is the number of successes, p is the probability of success, and q is the probability of failure. So n is 12, p is 0.1, that makes q 0.9. You can also always just do 1 minus p. We kind of found it the other way around. It was given to us that it was 0.9 as a decimal for the seed to not to actually grow, which is not what we're interested in, so we don't consider that a success. And then we were taking that value and doing 1 minus q to get p, so it works the other way around as well. X is the number of successes, and so we're looking for 3 that don't grow. Okay. So now that we have all that, you can either do the formula using the mathematical calculation. You can also use binom.dist like this. Okay, so we have the probability that x is equal to exactly 3 will be found using binom.dist with 3 successes, 12 trials, a probability of success of 0.1, and false for cumulative since we are only interested in an exact number of successes. And so there is your answer.